Thank you, Tassos. Can you hear me well and see my screen?
Yes, everything's fine.
So I'll be going. So hi everyone, I'm Jordan, and I'll be talking about how tariffs can impact low voltage distribution grid, and especially regards the penetration of PV and batteries in this grid and their operation. So to give you a little bit of motivation, so as we know, photovoltaic energy is expected to be one of the pillars of the energy transition. Most PV will be as a form of distributed rooftop PV because for dense area like Switzerland, we don't have enough space. This will lead to a high PV penetration in low voltage grid, which may raise concern about the safe operation of those grid. We know we can add batteries and use smart curtailments to mitigate the negative impact, but we need to make sure that we guarantee the return on investment of PV and battery system. And this heavily depends on the financial condition, which are the tariff actually. Currently, tariffs only promote self-consumption, which is for now the main PV system owner paradigm, and there is no incentives in providing a more grid-friendly operation of your system. And thus, we think there is a literature gap in studying the co-development of PV and batteries and their impact on low voltage grid, and that's what I'm going to talk about now. So our approach is to use an optimization formulated as a mixed integral linear programming to optimize the PV size and the battery size for each building in a low voltage network. And given this and the physical model of the low voltage network, we're able to assess the technical and economic performances of each system. And also by solving the load flow problem, we are able to assess the grid impact. And when we did that, we changed the tariffs, and then we calibrate the tariff in such a way that under the assumption that for the same design and operation of all systems, we change the tariffs parameters so that the revenue for the distribution system operator remains roughly the same, and we go back to the optimization phase to solve the whole procedure again and again. A few words about the building optimization. As an input, it takes the electrical demands, the irradiance, PV and battery cost function, the tariffs, and some general parameters like the interest rate and system lifetime. We send those information to the MILP, and we get the optimal PV capacity, the optimal battery capacity, and the resulting import and export power for each building in the grid. We do that for 1 year using real data at 15 minutes resolution. Let's have a look at the objective function. So we started from the standard minimization of the total cost of ownership, which is composed of the annualized capital expenditure and the operating cost. And we decompose this operating cost into several tariff structure. The first is a volumetric tariff, in which you pay as much as you imported energy, and you will earn money as much as you exported energy. We have a capacity tariff, in which you pay according to the maximum power, regardless if it's import or export, and it's charged monthly. And finally, we have what we call a Bloch rate tariff, which is actually a piecewise linear cost function I'm going to detail now. So as I said, the Bloch rate tariff is a piecewise linear cost function. So the cost function is composed of many linear affine function, in which the AK component, which is the slope of each linear component, is the marginal cost of importing energy. Okay, and the BK component, which is the intercept here, just ensures the continuity of the cost function. So as an example, if you're importing energy at 3000 watts, you will pay the first 2000 watts, something like 10 cents per kilowatt hour, the A1 component, and the remaining 1000 watts at A2, 25 cents per kilowatt hour in this example. And this gives you the value, the instantaneous cost of importing power at 3 kilowatts. Let me detail the key performance indicator that we use in this work. So first we have the PV hosting ratio, which compares the installed PV capacity with the maximum installable PV capacity, which is given by the size of the roof. We have the PV penetration. We know it compares the PV generation with the uncontrollable electrical load, electrical demand of each building. We have the battery autonomy ratio, which compares the size of the battery with the mean daily electrical demand. In other words, if you have a battery autonomy ratio of 0.5, it means that you can cover half of your mean daily electrical demand by discharging the battery. PV curtailment ratio compares the amount of energy that has been curtailed with the total maximum PV generation. We define a grid usage for import and export that compares the maximum import or export power with the maximum power of the electrical demand of the building. If you have a grid usage that is larger than 1, it means that due to the installation of PV and battery, you have actually increased how intensively you interact with the grid. And finally, the two remaining KPI are the discounted payback time, which will tell you in how many years you will recover your investment, and the self-sufficiency that is well known. We just formulated this in a generic way so that we don't need to care about how much PV or battery is inside. That's a case study. That's a low voltage grid in the Rolle area near the Geneva Lake. It's a small town. On this map, you can see the orange circle, which represents the potential PV capacity, and the yellow circle represents the annual energy demand. And it's done in such a way that if the orange circle is larger than the yellow circle, you have a PV penetration that is greater than 1. We took the forecasted cost for 2025, which leads to a PV cost of 1 Swiss francs per watt and a battery cost of 230 Swiss francs per kilowatt hour. This is our reference scenario. Nothing special, it's a standard volumetric flat tariff. So tariff is constant on the day at 21 cents per kilowatt hour, and your export tariff is 8 cents per kilowatt hour. We define then a solar tariff scenario in which the electricity price is cheaper during a period of high PV generation. Same for export. So this means that you have high incentives into self-consuming energy. It's a time of use tariff. So from 11 a.m. to 3 p.m. Every day along a year, electricity is cheaper. So you have interest in self-consuming PV generation. Then we have a spot market tariff, which is a simple mirror of the spot market price. Again, it's calibrated in such a way that under the assumption that all systems are the same as far as the reference scenario, and they operate in the same way, the revenue for the DSO remains approximately equal. And this just brings some volatility in the electricity price, which creates, we will see, more economic case to make profits. Then we have the capacity tariff, which is actually a mix between a flat volumetric tariff at 16 cents per kilowatt hour and a capacity rate. So you will pay the maximum power here, export in this case, at 5 Swiss francs per kilowatt. And finally, we have a Bloch rate tariff in which the import tariff increases with the power, while the export tariff actually decreases with the power, leading to a marginal revenue of exporting energy of less than 1 cent per kilowatt hour when you're exporting on more than 8 kilowatts. And this brings even more volatility in the electricity price. Now let's have a look at the impact of tariff on the design of the system. So what you can see here is a parallel coordinate plot. You have the metric here, and you have the value on the vertical axis of each corresponding metrics. The lines represent the median over all the building, over all the system in the network. And first observation that the PV hosting is always 1, except for the Bloch rate tariff, which promotes much smaller PV installation. The dynamic and capacity tariff promotes larger battery size. We'll see why in a minute. While for the reference and the Bloch rate tariff, the battery size is much smaller. And finally, we can observe that the grid usage is higher when you play on the spot market scenario or the solar tariff scenario than under the capacity and Bloch rate scenario, in which you are able to reduce how intensively you exchange power with the grid. One final comment on the discounted payback time here. It seems like the DPP is higher for the Bloch rate, but I can tell that the variance across system, which is not pictured here, is very important. On the left graph, you can see the self-sufficiency as a function of the battery autonomy ratio. And we can see that there is a general trend that the battery size helps to increase the self-sufficiency. So the higher the battery autonomy ratio, the higher the self-sufficiency. On the right chart, you can see the battery autonomy as a function of the PV penetration. And we can see that the battery size actually increases as a function of the PV penetration only for the volumetric dynamic tariff. For the capacity tariff, however, we have a much higher battery size for a system which have a low PV penetration. And this is due to the fact that at low PV penetration, what dominates your maximum power is the import peak power. So you will need the battery to cut this power peak, and you will then need a very big battery. As for high PV penetration, as we will see in a minute, you can use curtailment. You can just curtail your PV generation to reduce your export peak. And this is highlighted in this chart when you see the PV curtailment as a function of the PV penetration. And there is a clear trend showing that the higher the PV penetration, the higher the fraction of the energy that you have curtailed. We have a little bit of curtailment under the spot market price because sometimes the spot market can be negative and you want to avoid selling energy at negative price. On the right chart, you can see a map showing the grid usage export versus the import grid usage. As you can see, for the spot market, most of the points have grid usage that is higher than 1, both for import and export. And this places those points into the energy trader category. As for the spot market and capacity, as for the Bloch rate, and capacity scenario, most of the points fall in this area where the grid usage is smaller than 1, meaning that the user interact less with the grid. We call that low grid user. Let's have a look at the network impact on the load duration curve. This is the power transformer and the number of power along the year, and also the voltage deviation. We split it between when you have a voltage that is above 1 per unit, meaning that you have a local excess of energy, and when it's below 1 per unit, when you have a local deficit of energy. And as you can see, dynamic tariff, especially spot market, actually increase the stress on the grid, while Bloch rate and capacity scenario are able to reduce significantly the stress, the voltage deviation, and the stress on the grid. To conclude, to investigate the relationship between the tariffs, the system design, the profit and the profitability, and the grid impact, we used MILP approach to find the optimal design and operation of a collection of PV battery system. We customize the classic objective function to declare more advanced tariff structure. We analyze the system response and the network response to 5 tariff scenario, and by solving the load flow problem. And we can claim that dynamic volumetric tariffs promote investment in larger storage, create economic opportunity to recover storage investment, but also increase the stress on the grid. Capacity-based tariffs change the battery usage from trading energy to reducing consumption peak, and Bloch rate tariff promotes smaller PV installation, hence helping reducing the stress on the grid. As an outlook, we would like to investigate how the synergies with power to heat or electromobility change this conclusion. What is the typology of the prosumers that will contribute to the recovery of the grid cost? How can we optimize the tariff structure to promote flexible grid resources? And can we ensure to the distribution system operator that the revenue will be the same at all PV penetration? And with that, I thank you for your attention. I will be happy to take your questions.
Thank you very much, Jordan. There is one question posed by Rahul Gupta. Thanks for a nice presentation. For the prices, why don't you consider battery converters cost, which is generally of the same order as battery cost and can't be neglected? This will potentially affect the battery size and payback time.
Very interesting question. So if I go back to the slide about the cost. So in short, this can be included in the fixed cost. So in the fixed component of the cost function for the battery, let's say, that whatever the capacity of the battery that you will install, you will need to pay someone to install an inverter and use the electrical connection. And this, I can find the, yes, here it is. And this can be integrated in the battery fixed cost. So we were not able to find those data. So we just put that into the PV fixed cost. Does that more or less answer your questions?
Thank you. There's another question by Mohammad Darayati. Thanks for the presentation. For the grid, I guess you did not consider the voltage limits. Am I right? However, in high penetration of PVs in distribution grid, considering the voltage limit is an important factor. What do you think?
So indeed, what we did is really a parametric study. So we first optimize for each building what would be the ideal PV capacity and battery size in their operation, regardless of the network constraint. And then we assess the impact of this system on the voltage deviation. And indeed, it's clear. So it's clear that you as you have over voltage and the breaking of the voltage limit. So it's not that we didn't consider that. It's just that we wanted to investigate if we let the system free to do, if we let the system, the prosumer operate as they want, and the system operate as they want, we will have over voltage, and that's what we wanted to investigate. And if just by playing on the tariff, we are able to reduce this voltage, this over voltage.
Oh, thank you, Jordan. It seems there is one more minute. I could ask a question, but only if you could answer it within a minute. Yes. What are the implications of modeling uncertainty in PV production and load in your methodology? So
indeed, we didn't make a stochastic optimization. So instead, what we did is to optimize the post-design operation in a single problem for 1 year long. And we can more or less assume that all situation or a wide range of scenario is covered by optimizing the operation for 1 year long at 15-minute resolution. But indeed, it's not explicitly taken into account.
Thank you, Jordan. How unpolite of me. There was a posted question. Thank you from Mads Almasalki. Thank you for any curtailment. Was it spread equally across PV users?
I would say that I have the results, but just to remember. So as far as I remember, the larger the PV installation, the larger the PV curtailment. And it depends on the tariff scenario, especially for the capacity and for the Bloch rate. The PV curtailment ratios was much higher for large PV installation. As for the volumetric tariff, you have a more equal spread of the PV curtailment ratio.
Thank you, Jordan.